Question 2a says to prove by induction that this summation is true for any natural number. Let me just quickly start by going over induction. Induction is the idea that if you have some fact about A, then it implies that the same fact is true for B. That's all induction is. In practice, what will happen is you'll have some list of numbers. So let's say the first one is L, and induction, let me just say that this star means the induction relation will imply that it's true for the next one in the list, so M. And because L and M are no particular numbers, you can then apply the same induction relation to say that N is true. And you can just keep doing that for all the numbers in your list. Normally what will happen is, and in this case as well, is you're given, say, the natural numbers. So you take some k that's in the natural set, and you use induction to say that the same thing is true for the next one in the list, which, because they're natural numbers, is going to be k plus 1. Then the next one in the list is going to be k plus 2, and so on. The issue is that the truth of this, and the truth of this, and the truth of any number down the list is reliant on the fact that the number before it also had this relation. So k plus 2 is, so this statement, this fact, is only true for k plus 2 if it's also true for k plus 1. And it's only true for k plus 1 if it's also true for k. But then we don't have anywhere further to go back. So it has to be true for at least one number before induction will actually work. And generally what will happen is you'll have some starting point to go with. In this case, you can see you're starting with 1, and that makes sense because 1 is the lowest of all the natural numbers. So you'll have some fact to prove about 1, or it might be 2 or 3 or whatever, but in this case, let's say 1 is your starting number. So you can prove numerically that this idea, this fact, is true for 1, and then because you've proved this induction relationship, that then you can actually apply that to 1, and that will tell you that the fact is also true about 2, and then the fact is also true about 3. So then it's true for all the numbers, all the whole numbers that are higher than 3 as well. So then it's true for all of the natural numbers. So like I say, first of all, we need to test if this statement is true for n equals 1. The left side is that you sum up all these values. In this case, the only value there is 1. So 1 is equal to 1. There you go, you're done. The right hand side then is n times n plus 1 over 2. In this case, n is 1. So we just sub that in, we get 1 times 1 plus 1 over 2, which is 1. And with proofs, they really like these finalizing statements, so you say, so this sum here, this summation, is true for n is equal to 1. The next stage is to assume that the statement is true for some particular n equal to k, we'll call it. So the sum of all the r's from 1 up to this number k then is 1 plus 2 plus 3 plus and so on, all the way up to this number k. And we're assuming the statement is true, so all of this is equal to k times k plus 1 divided by 2. Next we want to test if it's true for the next one, k plus 1. And to test that, we're going to just see what the value of the summation is for k plus 1. Well, it's 1 plus 2 plus 3 plus and so on, plus k plus 1. And right before k plus 1, which is just this one entity here, really I could probably have brackets around it,
and so right before k plus 1 is just k itself. And remember, we're assuming that the summation up to k is equal to this thing. Well, that's what I have here. So I can say that all of this stuff up to k is equal to k times k plus 1 over 2, and then all I have left at the end is the k plus 1 here. So that's half the job done then. Anytime you're doing induction, you're almost definitely going to be replacing something in your summation or whatever it is you're trying to prove with something from your assumption. So now we've got this here, the k times k plus 1 over 2 plus k plus 1. Don't forget, this is a proof, so you're actually given the answer, and you know what you have to get in the end. It's like looking at the back of the textbook to see what you're meant to get at the end of the question. Well, this is what we're trying to get here, k plus 1 times k plus 2 over 2. It's this thing, but instead of k we have k plus 1, and instead of k plus 1 we have k plus 1, which is k plus 2. So the first thing to notice really is this isn't all in one fraction, and this is all in one fraction. So I'm going to try and get a common denominator here, and to do that I'm just going to multiply by 2 over 2. Remember, this is an expression. Even though this is an equal sign here, this is still just an expression, so we can't change any values. So I'm just multiplying by 1 here, so I'm not changing any values, I'm just changing the way it looks. With that then, I guess k times k plus 1 over 2, which is what I already had, and then I guess 2 times k plus 1 over 2 here. And notice here that the k plus 1 is common in both terms, so I can take that out as common, and I get k plus 1 in one bracket, and then I get whatever's left in another bracket, so I get k and the plus 2. So there's k plus 2 there, and the divided by 2 is still there. And that was what I was trying to get, so that's the whole question finished. If you don't recognize that the k plus 1 here is common, you can also just multiply everything out, and you'll end up with a quadratic, which you can then factorize, and you'll be able to get this. So just to finish off the question then, just remember you need your finalizing statements. They love finalizing statements in proofs. So since we got this thing here, which is what we were trying to get, that means that this summation thing is true for n is equal to k plus 1. And since now, if it's true for n is equal to k, it has to be true for n equals k plus 1. That's what we've proved. And since we know it's true for n equals 1, that was the thing we tried to write at the beginning. By induction, it's true for n is equal to 2. And since it's true for n equal to 2, then it's true for n equal to 3. If it's true for n equal to 3, it's true for n equal to 4, and so on, so on, so on, up to infinity. So then, by induction, this summation is true for all n greater than or equal to 1 in the integer set, which is pretty much the same as n in the natural set, which is what you were asked to prove in the first place.
Question B asks you to state the range of values of x for which this thing is convergent, and to write that infinite sum in terms of x. Now, first of all, there is some question as to whether or not this is something you actually need to know, but for the sake of completion I'll go through it all anyway. First of all, let me just go through the idea of convergence. What's going on here is we're adding up a load of numbers. So we're starting with A, and then we're adding on B, and we're adding on C, and we're adding on D, and we're just adding on loads and loads and loads. And it doesn't stop at Z, it goes on forever and ever. So what's happening to the size of this thing? Well, we're starting with something that's this size, and then we add on the B, so we get something that's a bit larger, and then we add on a C, so we get something that's a bit larger again. All of these are positive, let's say, so we're always getting larger and larger. Then we add on the D, and we get a bit larger again. Then we add on loads and loads and loads more numbers, and we get something that's really, really, really big. We keep adding numbers to that. Doesn't stop. Convergence is the idea that even though we're adding on more and more numbers all the time, and this thing is always getting bigger, there is some hard cap on the size of this. Some boundary, some limit. The size of this infinite sum is never going to be bigger than this boundary, this limit. How can that possibly be? I mean, we're constantly adding on more stuff to this. It's always getting bigger, and we're always adding more stuff. So how can it never, ever get past this boundary? Hopefully it will make sense to say that eventually the number we're adding on, let's call it, let's say t. T is just a general letter I'm using. It's not a particular number I'm adding on, it's just any letter that I'm adding on. Eventually the size of some letter that I'm adding on is pretty much 0. So if I'm adding on, well, not quite 0, but almost 0 to this thing, it's still getting bigger. I'm adding on, 0.000001. It's getting a little bit bigger, but it's not getting so big as it's going to go past this. And the number I'm adding on keeps getting smaller and smaller and smaller. But it's always still positive. So this thing is always getting bigger. But each time I add on a number, it's not getting as big as it did the previous time. So, my numbers, my box is going to be a little bit bigger, a little bit bigger, a little bit bigger, and it's never ever going to get past this black box here. Now this isn't the only qualification here, that I'm eventually adding on 0. It's possible that I'm not getting to 0, I'm not getting really close to 0 quickly enough, and whatever boundary I set for this infinite sum, eventually I will pass by it. So this isn't enough to say that something converges, but if something does converge, then this is true. In terms of eventually writing the infinite sum in terms of x, well, it's just on page 22 of your table book, there's some formulas there, and I'll go through them in a few minutes.
Here's what we're given then, the 4x minus 1 to the power of r. For what values of x is this going to be convergent? Since we know it converges, the question says it does converge, and we just want to find out which values of x will make it converge. It's going to be true whenever we're eventually adding on 0 all the time, or pretty much 0. So when are we going to be eventually adding on 0? If we're taking something to a really, really big power, this r is going to infinity, then when is something to the power of a very big number very close to 0? Well, it's when the thing you're taking to a power is less than 1. So here we go, the 4x minus 1, and don't forget your modulus here. So just follow that through, and we get minus 1 is less than 4x minus 1, which is less than 1. You can do these inequalities separately, but just for the sake of expediency, I'll just do them all at once. So I'm adding 1 everywhere, so plus 1, plus 1, plus 1. So I get 0 is less than 4x, which is less than 2. Then I divide everything by 4. So divide by 4, divide by 4, divide by 4. And so I get 0, and I get x, and I get 1/2. So these are the values of x for which this thing is going to be convergent, because we're eventually adding on pretty much 0. And again, just for the sake of clarity, if you're eventually adding on 0, it doesn't necessarily mean it's convergent. It's only because we're told it's convergent that we can say this. Then we're asked to find what the infinite sum is, and this formula is just in your table book, so you can use that. This formula is for when we're adding from 1 up to infinity, but we're not adding from 1 up to infinity. Remember, this is the formula for one term. We're starting at this power here is equal to 2, because r is equal to 2 there. Oh, and don't mistake, this r and this r, they're different. In this case, r is the 4x minus 1, and the n minus 1 is my r. So if this n minus 1 is 2, if the first term is 2, then n minus 1 is 2, so n is 3. So my first term is t3, and I also have the t4, and I'm adding all of those up. So then instead of finding the infinite sum, I'm finding the infinite sum, but I'm not including t1 and t2. So to work that out, I just take the infinite sum that's starting from n equals 1, going up to n is equal to infinity, and then I'm taking away the first two terms because they're not included, because I'm only starting at the third term. So this here is a divided by 1 minus r. A is 1 in this case because we have nothing beside our 4x minus 1. And then the 1 minus r is just 1 minus the 4x minus 1. Again, just don't confuse the r that's in the power in this particular question and the r that's given in the formulas. So I'm going to take away the first term. Well, the first term is 4x minus 1 to the power of 1 minus 1. And this is going to be the power of 0, which means that my first term is 1. Remember, things to the power of 0 are 1, they're not 0. So t2 then is 4x minus 1 to the power of 2 minus 1. That's the power of 1, which means it's just 4x minus 1. So I put in my minus 1 and my minus 4x minus 1 here. I do a bit of a cleanup. This plus 1 here, and this is going to be a plus 1, so I'm going to get a plus 2, and I've still got the minus 4x. This is going to be minus 1, this is going to be minus 4x, and this is going to be plus 1. So that minus 1 and that plus 1 are going to cancel each other. So all I have is 1 over minus 4x plus 2 minus 4x. And you can probably stop there. Let's say though you're like me and you can't stop there. You need to see if this is going to clean up and become something a little bit nicer. And even if it doesn't, then just the notion that you've tried is enough. You can do it this way. Just multiply the minus 4x by the minus 4x plus 2 to get a common denominator. So you get this, cleans up into this quadratic expression, which you can then factorize into 4x minus 1 times 4x minus 1. And unfortunately that's not going to cancel with anything on the bottom. That's a real disappointment. Well, anyway, at least you know you can just stick with this here.